Okay, so this is, I presume this is not presume, I know that this is one of your first design course on circuit synthesis, circuit analysis, and circuit design. So what we'll do is we'll start off with something that is very basic. Okay. So as I said, when I showed the introductory slide, where we will end up is some contraption which is essentially an amplifier. And one of the reasons we choose amplifier for basic circuit design courses is because an amplifier is essentially a workhorse for analog circuits. So none of the building blocks that I have shown you in the slides before, you cannot find one building block which doesn't use an amplifier of some sort. The specifications might be different, but what does an amplifier do? Yeah, what is essentially an amplifier? Anybody? Right. So amplifying means controlling amplitude. So now, if let's say when I say amplifying the signal or increasing amplitude, so can I say that something like let's say I give a 1 volt input, right? So this is my system. This is input, and this is output, V out, VO, V out. So I give a 1 volt input, and let's say I get a 2 volt output. Does it say that it has amplified something? Might be, might not be. Very good question. Answer. Why do you say so?
It might have a battery.
Right. It might have a battery. So as he pointed out, that it's possible that I might have a battery in between, which is giving me the 2 volt output. So does that say that I have an amplifier? What if I say it is an amplifier inside? I'm giving, as far as for all practical purposes, I see that this is an isolated system in the box. I'm giving 1 volt, I'm getting 2 volt output. Why not an amplifier?
So amplifier have control sources, dependent sources.
Right. Okay. Amplifiers have dependent sources, or amplifiers require dependent sources? Yeah. So now as we go through the course, we'll see why they require dependent sources. Can we make amplifiers without dependent sources? Is it possible? So is there a property of an amplifier that necessitates the use of a dependent source? What is it?
Output depends on input.
Output depends on input. Output obviously has to depend on input, but does that again mean amplification? Output depends on input means that there is a necessary relation between how the input changes and how the output changes, right? Which is essentially correct, which is a necessary condition, but is it a sufficient condition?
Independent sources add to the voltage, but dependent sources help in multiplying the voltage.
Independent sources add to the voltage, and dependent sources help in multiplying the input voltage. Okay, can you elaborate on that? You are on the right track, but I want to understand the thought process. Can you elaborate?
So we use dependent sources so that we can add a gain factor to the voltage.
Okay.
Voltage or the current.
Correct.
With this we get the amplification.
Okay, great. So what he is pointing out is that we need a gain factor. That essentially is the key term, right? We need a gain factor. So now question is, how do I get a dependent source with a gain factor? Using external sources. So which is something not inside the box or outside the box?
Inside the box, but
okay, so when you say sources, let's converge on a terminology. When you say sources, do you mean a battery kind of source, or something that you see in laboratory where you have a signal source separately that you turn the knob to increase the amplitude? That type of battery. But let's assume this stuff inside doesn't have a battery. Then all the batteries are outside. Then is this an amplifier? As it turns out, one can argue that this is an amplifier, but this is not the sort of amplifier that we will be designing in this course. Okay, so take it from me that this can be I mean, if you don't have a battery inside and you are applying 1 volt and you are getting 2 volt, this is increasing whatever you have applied, right? So in a sense, it is an amplifier. Yes.
Sir, if there is no battery, then how can the voltage?
Good question. So how can I explain to you right now? I would like to come back to you after some time, but let me try and explain. So you say that if there is no battery inside, how can I go from 1 volt to
Battery means source.
yeah, basically a DC source, right? Any DC source. If you don't have a DC source, how can you go? So why do you say that a DC source is essentially required to amplify? That's essentially the other question.
For controlling, for the use of bias, used bias.
Right.
To control.
But is that the only way? What are you assuming? For whenever all of you are right, but you are assuming something at the back end when you are making these statements.
Power.
Yeah, energy, power, right? But what else? You are inherently assuming something about the system that you are not spelling it out. Linear, exactly. You are assuming linear system. So why am I harping on linearity? I'm harping on linearity because see, when you are applying some voltage, and let's assume your system inside is nonlinear. Okay, so let's assume your system inside is nonlinear. You have applied a voltage. When you have nonlinear, now think in terms of frequency domain, in terms of convolution, frequency shifts, and so on. So think in those lines. So let's assume it's a nonlinear system. You have applied an input at certain frequency. Okay, it's a nonlinear system. Give me an example of a nonlinear system, some equation. X squared, something, y equal to x squared, v out equal to v in squared, something like that, right? So if it's a nonlinear system, then, and I give a sinusoidal input, let's say, again, I mean, it need not be sinusoidal, let's say I give a sinusoidal input, sine omega t. What do you expect the output frequencies to be? 2 omega, right? So which means there is a frequency shift that has happened. Now, this is just an example that I took. Now, it's quite possible that I have a system where I give an input which is at different frequency and comes back at different frequency. And if I observe and that different frequency, the final difference frequency, let's say is DC, then it's quite possible that I take some frequency components, up convert it to some other frequency component, down convert it to DC, and whatever is the resultant is something which is more than the input. Possible, right? Okay, so what I essentially trying to get at here is that, let's say you have a multiplier inside. How you have made the multiplier is not a part of this course. Even this is not a part of this course, but we are, since we are asking these questions, let me go ahead. So let's assume we have a multiplier, okay? And let's assume, this multiplier is such that you have a one input sinusoid, right? And let's assume you have another input here, some other frequency or same frequency, I don't care. Let's assume same frequency for the timing. Let's say omega naught, omega naught. What do you expect the frequency components of the output to be? Only 2 omega naught? If you break sine squared, what do you get? You get 2 terms. You can get a DC also, right? You can get a DC also, right? So let's say if this DC, in the input, you didn't have any DC. Input are pure sine. The output, you can get a DC, right? So now let's say for all practical purposes, I put a band pass filter or the low pass filter at the output, and I am only observing DC. And I maybe had some DC input on top of this, maybe some, let's say 1 volt. And I observe the DC at the output. I say that the DC at the output is more than 1 volt. So what can I infer? I can infer that maybe my input had a 1 volt DC, right? And output has more than 1 volt DC, so it can act as an amplifier, right? The inference is correct, but we will not be going into these type of systems in this course. These type of systems are often called periodically time varying systems or time varying systems in general. We have separate course for that. An elective, if you're interested, you can take it, but not a part of this course. But the key takeaway from what I wanted to convey here is that we are essentially looking for, when you said that my input is 1 volt, output is 2 volt, not possible without the battery, inherently what we assume, this is, we are assuming linearity. Not only we are assuming linearity, we are assuming linear time invariant circuits. Right? Both are important because time variance can also cause frequency shifts. And time variance means that when you multiply, you are essentially doing time variance. I mean, since you have taken E200, I presume you know that multiplying operation is not a time invariant operation. You know that?
Yes,
Okay. Okay. Even if you don't know that, don't bother. But so what I'm essentially saying is that this course will deal with linear time invariant operations. Okay, so or LTI operations, or let me just call it systems. Okay, so but as it turns out, I mean, some of you alluded to initially that we need to have some things inside the system to get an amplification with LTI systems. And again, why it is necessary to have something different, different inside to get an amplification in LTI system will be clear at a later class. But for that time being, take it from me that you cannot design an amplifier with a simple LTI system. It's simply not possible. Okay, you need some sort of nonlinearity or some sort of time variance inside your box to get amplification. Again, why? I'll come back to it at a later stage, but take it from me at this time that it's not possible. Now, some of you might say that, hey, I mean, you know so many control sources, voltage control voltage sources, voltage control current sources, they are LTI systems, right? Yes. Then why am I saying that? I'm saying that because the purpose of this course is to design those voltage control current sources or voltage control voltage sources. I'm not assuming they are available. I'm assuming the simple L, C, R, these type of thick stuff are available, but or even diodes, MOSFETs, BJTs, this type of stuff elements are available. So is it necessary for us to take the help of those diodes, MOSFET, BJTs, or can we make an LTI system? Can we make an amplifier with an LTI system without their help? Right? As it turns out, you will require the help of those diodes, MOSFETs, BJTs, or in other words, some nonlinear element, not necessarily only limited to diodes, MOSFET, BJTs, but you will require the help of some nonlinear elements in order to make an amplifier. Again, these are all storytelling at this junction, but I'll come to that in a more rigorous manner in a later class, right? So now the question begs that how do we analyze a nonlinear system? Because if we have to use some sort of nonlinearity, so we need to have some mathematical framework to analyze a nonlinear system. Now, I don't know about you, but I don't know of any mathematical framework that allows me to design and deal with nonlinear systems in an analytical way. In most cases, you'll have to resort to some sort of numerical solvers or some iterative methods to analyze any nonlinear system, right? So now, if that is the case, and obviously, I mean, you can now look back at your journey till now, and you see that almost all the courses that you have taken deal with linear systems, linear set of equations. You have been doing linear set of equations in the last 5, 6, 7 years. You have been doing linear differential equations, Laplace transforms, Fourier transforms, all deal with linear systems. Then if in reality, there is nothing called, I mean, you cannot use linear systems to design a simple amplifier, then why do we spend so much time learning those, right? So there is a reason for that, and the reason will be clear in the next few minutes. So before we start with the analysis of nonlinear system, let me ask you, how do we identify a linear system, right? So let's say I have a system where this is V in, this is V out, And I say that my V out, V versus V out characteristics looks like this. Is it a linear system, non-linear system? Non-linear system, right? Okay. Again, why do you say so? It's non-linear?
V out dependency on V is not.
V out dependency on V in is not linear. Again, when you say non-linear, what do you mean?
So we
Slope is constant.
Slope is not constant. It's not a straight line. Okay. So let me change the graph. Yeah, good. You are correct. So it's not linear. Let me change the graph and say something like this. Still not linear. Why not?
Not passing from origin.
Not passing from origin. Good. Very good. So why is not passing from origin such a big deal?
But linearity, additivity, and homogeneity.
Right. So linearity is additivity and homogeneity, which essentially means that if in this case, I should be, if I have an input, if fx transforms x to y, I should have the relationship between x and y such that, let's say for set of inputs x1, it gives y1, for x2, it gives y2. Then if I apply an input alpha x1 plus beta x2, I should be getting alpha y1 plus beta y2. Great, right? So now it's good that we are on the same page. So we can then proceed. So now let's take a generic nonlinear system. Okay. So let's take a generic nonlinear system. And instead of taking any generic nonlinear system, let me take like an example, right? I'll come to a generic nonlinear system later on, but let's do it with an example first, then we will get to generic nonlinear systems. So let's assume that we design a simple circuit, right? We design a simple circuit which has a single nonlinear element. What is the simplest nonlinear element that you have studied till now? Diode, right? Great. So let's assume you have a resistor and you have a diode. This is V. Oh, that's not it. So that's the battery. VA. So again, before proceeding, just to ensure that we are on the same page, in order to analyze this circuit, we require the help of KVL, KCL, and what else? Diode characteristics. So essentially, to analyze any circuits, you need three things. One is obviously the good old Kirchhoff's laws, and the third thing is the relationship of the current voltage relationship or the IV relationship of all the elements in the network. Given these three things, in principle, we should be able to analyze any circuit. Okay. So what is the current voltage relationship of a diode? Okay, so let's say this is VD. ID equal to some constant, let me call it IS, e power. So all of you know this. Anybody who doesn't know this relationship? Because I'm assuming that, there are folks who are taking double majors and all, right? So, okay, fine. If all of you know this, then I won't spend too much time on this. So, what is VT? Yeah, it is KT over Q, and we generally approximate it to 26 millivolt at room, right? At 300 Kelvin. Okay, so and IS is some constant which depends on the way the diode has been constructed, right? So this is constant for a particular diode at a particular temperature. Again, I mean, this IS also is temperature dependent. Again, I mean, if you want to understand how these things came into being, that falls in the domain of device modeling courses 311 and so on. So you can, I would encourage you to go through. I mean, register for those courses when the time comes. As of now, we will be dealing with nonlinear elements as black boxes, but the relationship between I and V is established, and this is the relationship between I and V of a diode. Good. So now, so given that this is the equation at hand, this clearly tells us that if VD is, let's say, slightly more than VT, VD is, let's say, 2 or 3 orders of, I mean, if VD is VT itself is about 26 millivolt, and if VD is, let's say, 52 millivolt, 100 millivolt, etc., of that order, then I can neglect that -1 term and I can simply approximate ID to be equal to IS e to the power VD over VT. So this is under forward bias condition, right? That is, VD is much greater than VT. Now, what is much greater than is again up to us, but again up to us and up to the application that warrants it. So essentially, as we will again go along engineering courses, you will see that engineering is essentially the art of making approximations, right? So certain approximations hold under certain conditions, and certain approximations do not hold under certain conditions. What differentiates a good engineer from a not so good one is to understand when these approximations hold, right? A very trivial example in this case is if I sketch the ID and VD for this diode, this will look like something like this at forward bias condition, but at what happens at negative VD? Yeah, it will saturate to IS, right? To minus IS, right? So what I meant is essentially this equation, you cannot use this equation you cannot use this approximation for reverse bias condition. Again, so very trivial example, but example nonetheless to point out the fact that given a set of equations, you need to know what to use when. So under forward bias condition, we can approximate the IDVD characteristics of a diode as this. Okay, fine. So now that we know this IDVD characteristics of this diode, let's go back to our circuit. So now help me through, how do I set up the analysis so as to understand what is the diode voltage? If let's say the diode voltage is something of interest to us, right? How do I set up my analysis in order to figure out what this diode voltage will be? Help me out. Okay, we have to write KVL equations, and okay, help me out through the KVL.
VA equal to IR.
Okay, so let's assume that we have a current, say I1. Okay, so let me call this V1 because it will be consistent. Okay, so V1 will be equal to I1R plus VD. And what will be VD?
Assuming forward bias.
Assuming forward bias.
IS VD.
So given that I have this equation, your VD will be VT times ln of ID by IS. All right. In this case, if it's I1, so this will be equal to okay. So now obviously you see that we have run into some sort of problem. We end up with we are stuck with a transcendental equation. Right? Clearly, this is nonlinear. So again, you'll have to either take out your log books. I'm not sure you even heard of that. So, or you do some sort of numerical solver, Newton-Raphson, or if you have to do it by hand, you start off with assuming some initial bias condition, and then you iterate and see that each iteration you get closer and closer, right? So what I am getting to you is that with a simple R and a diode, things are already messy enough. Why? I mean, then how do we plan to do anything if we have more of such things and more of such equations, which are maybe something is a square, something is an exponential, something is a linear, all jumbled together. How do we go about making our life easy, right? So there is indeed there is a way of making your life easy. So let's assume that you have used your numerical solver, or you have used your iterative method once to put in that effort and figured out what is this V1 and what is this I1. Right? Let me assume that. Assume that we know what V1, I1 is using some iterative process. Okay, so let's say that we have put in some effort and we have figured out what is this. Then I come to you and say that I will just change this. This is not something I want. I made some mistake in hooking up my circuit, or maybe I don't want V1. I want here, instead of V1, I want V1, and maybe I want V1 plus delta V. Okay, so I want what is this new VD? So this is VD. This is VD2. Right? I have a separate input voltage, so I expect a separate output voltage also. I expect a separate output current also, right? So maybe this new current is I2. So what will this new equation be? It will simply become V1 plus delta V will be I2R plus VT ln of I2 by IS. Now what? We go through the same process again, we iterate again and figure it out, or can we do something smart? What do you think? Can we do something smart? For small delta V? Right. Okay, so let me ask you, I mean, okay, so maybe I could ask on a generic level that are you aware of small signal analysis? All of you? Okay, fine. Then I will not spend much time, but I will go through it quickly. So essentially what I am getting to here is that if V1 has changed from V1 plus delta V, I can say that the current also has changed, right? Current also has changed. Initially it was I1. Maybe it has changed from I1 to I1 plus delta I. Okay. So if that is the case, I'll simply replace I2 with I1 plus delta I. So what am I doing? I'm doing V1 plus delta V will be equal to I1 plus delta I times R plus VT times ln of I1 plus delta I by IS. This is one equation, and the other equation was V1 is equal to I1R plus VT. Okay, so now if I am interested to find out delta V, what should I do?
Directly, like remove the V1 source and I.
No, I mean, let's say I want to do it mathematically. I have two equations. I want to find delta V. I want to find what is delta V. I can simply subtract the bottom equation from the top equation, right? So So now, because you might say that I have ln A minus B is A by B, I can easily subtract and make my life easy. But recall that diode, as it turns out, is exponential. It need not necessarily be. It can be any good old function. Okay. So now, don't think of ln as a special function in this case. Think of it ln as some function, some nonlinear function. So if you have a nonlinear function, now I am pointing to this equation. If I have a generic nonlinear function which is defined at, let's say, I1, if I1 is defined, and I want to find out what is f of I1 plus delta I, what should I do? Taylor series, right? Taylor series. I mean, it's similar to, if you know your position and you know your speed, you know where you will be at the next instant. And if you're accelerating, then you have to know the second derivative, and then you add them up, right? With some weighting factor. That essentially is your Taylor series. So similarly, if you want to find out what is f I1 plus delta I, you'll have to essentially do. Now help me out with the Taylor series expansion of this. F of I1 del f by del I evaluated at I1 delta I plus at plus so on, right? Right. So now again we'll make an approximation. If we say that if my so if I say that this approximation, this stuff here, right? Whatever is the extra stuff other than the del I is much less than the stuff that precedes it, right? So in other words, if I say that del I is much smaller, I don't know, I haven't yet defined what del I is, but let's assume that you have imposed a condition such that del I is much smaller, or del I is so small that I can neglect these higher order terms. Then I can simply say that this is approximately equal to f of I1 okay. So then what do? I replace so in our case, our f is ln. So what will be del f del I? In our case, our function f of I is ln of I by is. So what will be del f del I? 1 by I, right? So let me just replace this here. So let me point to this equation and say that I will just replace this as V1 plus delta V will be equal to I1 plus delta I R plus f of I. What is f of I1 rather in this case, which is Vt ln of I1 by Is plus Vt by I1 delta I, right? And the other equation, the equation which was there before I applied this extra voltage delta V, was V1 to be equal to I1R plus Vt ln I1 by Is. Now it's trivial. You subtract the bottom equation from the top equation, and what do you get? If you subtract this, you get delta V to be equal to delta IR plus Vt by I1 times delta I. Okay. So now can you comment on the type of equation this is? It's a linear equation, right? So we started off with a nonlinear equation, a transcendental nonlinear equation, and we ended up with a linear equation. What did we do? What was the step in between? We made an approximation of a linear system, a nonlinear system, and converted it into a linear system, right? So essentially what we did, we linearized a nonlinear system assuming small perturbations. Right? So we perturbed the original system. We had some system set up which had a current and voltage relationship of V1 and I1. I perturbed the system and I applied this incremental delta V on top of the system. And I figured out that we argued our way through and we said that, and we figured out that the relationship between the incremental perturbation, incremental voltage that I applied, and the incremental current that resulted is linear. So now when you are in linear domain, you are in safe territory, right? You have all the tools that you have learned till now to analyze a linear system. Okay, so that essentially is the requirement of finding out, what helped us from going from the nonlinear system brought us to how do we analyze a linear system? It's Taylor series, right? So a Taylor series approximation helped us to come from a nonlinear system which is difficult to analyze to a linear system which is easy to analyze. Now, it's not only that, there are certain aspects to this relationship which is important. I will allude to that in the next class. But from your experience, let's say you are listening to music in a stereo, right? And you are not happy with the volume that it is throwing out. You want to increase the volume. You turn the knob, maybe not your slider. Let's say you turn the knob. You turn the knob by maybe 20 degrees. You expect the volume to increase by certain amount. Now, if you want to double the volume, what do you want to do? You would want to turn the knob by 40 degrees, right? So what essentially is happening is that inherently you are assuming a linear operation of the system, right? If the system that you were, if the audio player that you were handling was not linear, then first 20 degrees it probably will increase by a certain amount. Next 20 degrees it will increase by a different amount. And for an audio player which is not made very well, you will see that if you increase the volume to the end, it cranks, right? Sometimes it shrieks, it makes loud, weird noises. It's because stuff inside it is nonlinear, and these approximations of Taylor series that we did start to break down, right? So in some practical scenarios, if you are not careful, if you are not designed it well, your this delta V that you can apply can be so large that this approximation of higher order terms, neglecting the higher order terms, remain no longer valid. So the whole game here is to figure out, right? Is to find out what this approximation is and whether this approximation is valid or not, right? So again, this course is not deep enough for us to go into whether this approximation is valid or not. We will assume that this approximation is valid, and we'll see that given that those approximations are valid, what we can do and how we can go ahead and do our analysis. Okay, any questions? No? Okay, fine. Then we'll stop here. Thank you.